So what we have here is we have pure substances. Did I already cover this last time? No? Okay. So we have pure substances. This is going to be matter that's made up of only one type of substance. This can actually be represented by one chemical formula or symbol. Okay? And so this would be things like pure water, pure gold, uh, pure gold, 24 karat gold, I mean. Do you guys know what 24 karat gold is? It's a gold alloy used in rings. Because
I don't actually know the specificity of like what carat is. I know that
oh, it's okay.
like
So
meaning it with gold with it.
it's actually several different types of carats, but in terms of 24 karat, 18 karat gold, it's actually mixtures of typically steel and gold, and you mix the gold with other metals, so it's a little bit harder. So if you ever get actual gold, pure gold, it's very soft. Yeah, if you bite into it, it would actually deform to your bite. Yeah, and so if you used a ring for that, for example, and if I went like this with a ring of gold, I would have flattened that ring. It's very soft. You ever had pure copper, excuse me? They make like bracelets with pure copper, pure silver, where you can just like this and it bends around your wrist, right? Yeah, gold is similarly soft. And so carat is just it's a little bit more complex, but it's basically a mass percent sort of thing, where they're telling you the sort of mass differential they made the alloys made up. Yeah. Yeah. I'm just going to go that far because there's a whole history there. All right. So element, this is going to be the simplest type of matter. It's going to be made up of only one type of atom. And so we could have, for example, O2, which is oxygen. We could have H2, which is hydrogen. And if we have a pure sample of that, that's going to be an element. Okay. We could also have, for example, elemental carbon. And in fact, you may have actually seen elemental carbon, especially if maybe ever seen a lab-grown diamond. Okay, you've seen elemental carbon then. Okay, it's just a very specific arrangement of it, but yeah. Lab-grown diamonds are very pure, very organized structure, and so they're actually an element. Okay, or very, very, very close to. Carbon can also be in the form of coal, but it's very unusual to see a pure element coal, usually a mixture. That's if it was pure black coal, that is elemental coal. Okay, elemental carbon, very, very pure coloring. Your graphite and your lead is actually pretty close to a pure element. Not quite usually, but very close. Okay, as close as you typically will see in a day. Now, atom, this is going to be your smallest unit of matter that keeps its unique characteristic. This comes from the Greek atomos, which was actually a natural philosophical belief in the Greek times. They recycled that word for this. It's a pretty decent use of the word because it is the smallest you can split things up until they change properties completely. So if you split gold up any further than its atom, it's not going to be anything like gold. Okay? It's not really going to have any of the properties that you would associate with gold. A compound, this is going to be a pure substance. It's going to be made of two or more elements chemically joined together. And so this would be things like H2O. That's probably the one you know the best. Or carbon dioxide, CO2. Those are both compounds. Okay? Now, a mixture is going to be a combination of two or more substances. And so you've taken two or more of these substances and you mix them together. So, for example, coffee, you're mixing all the stuff in coffee, right? Which actually something like 20 to 50 different compounds. And then you're putting that into water and probably some sugar and cream and all sorts of other things, right? And so that's a mixture. Mixtures can be separated back out into their different components. In fact, I have a lab where people do that and take the caffeine out of coffee. And you can separate all the different components. If you've ever put soap into your coffee with cream, you'll see the cream come out on you when you're, cleaning it. Anybody ever put the soap first? Not do the water and all that? No? Ah. Now you gotta try it, okay? Next time you're cleaning your coffee cup, dump most of it out, but put some soap in there, and you'll see them split. It'll get much whiter on one end, much more coffee looking on the other. Okay? No. The homogeneous mixture, this is going to be homo for same throughout, right? And this is homogeneous mixture. It's the same throughout. You can't see a clear difference. Okay? Coffee is typically a homogeneous mixture. Normally, tea is a homogeneous mixture, assuming you did a good job keeping the leaves out of it. A heterogeneous mixture is going to be one the composition is not uniform. It's going to vary throughout it. The typical example most people would give would be like a salad. You have the leaves, you have the dressing, maybe some tomatoes, carrots, and you can see the difference between all of them, right? They're mixed, so it's a mixture, but it's heterogeneous, so you can see the difference, okay? You're actually surrounded by many, many, many homo and heterogeneous mixtures, okay? So, for example, our skin is a heterogeneous mixture. You can tell the different parts of it, right? There's, pimples and pores and hairs and all sorts of things. The ceiling tiles, those are heterogeneous mixtures, right? You can tell the difference between them. Your desks are heterogeneous mixture for that polymer on top. That's that plastic. Interestingly enough, if you look down for the black portion of your desk, that one's a homogeneous mixture because it's same throughout, isn't it? And that's the paint. Okay. And so you have lots and lots of these things all around you. Typically, most gold would be a homogeneous mixture that you've seen. It's a different, several different alloys that are making it a little bit harder for use in gold. But you can get heterogeneous mixture gold. And it has kind of a striped pattern to it. And they do that for that reason. It has a kind of pattern to it. So, yeah. So right here's the flow chart I want you to have in your heads, and this is going to be matter up at top, and that's almost everything that you encounter in a day, right? Does anybody know what the only non-matter thing is? It has mass, it has volume. What's the only thing you encounter in a day that doesn't have mass and volume? Air has mass and volume, right? So it's matter. Do we encounter something that doesn't have mass and volume, maybe? Sound. Sound is no. Sounds right. Sounds right. You're good. You're good. So sound is an expression of something, though, and that's energy. Energy. Yep. You were exactly correct. I just wanted the root of it. Yeah. Yeah. Which is the energy. The energy is the thing you encounter every day. Doesn't have mass. Doesn't have volume. Right. Yeah. And so that's the other half of this. Now, saying that matter, that's almost everything you encounter in your existence. So we probably want to break that down a little more, right? And so we break that down into pure substance and mixtures. Then we go mixtures. Well, that's going to be homogeneous and heterogeneous. Does anybody want me to say those according to the European way of saying it? Homogeneous and heterogeneous. Okay? It depends on exactly where they accent it, depending on the accent. But that's overall. Then if we go into pure substances, that's the other half of that matter, the other half of the stuff. And this is going to break down into elements and compounds. Okay. Now, the next thing we're going to start talking about is the periodic table. So this right here is the periodic table of elements. I'm going to kind of go back and forth between this one, which is a much more like stereotypical IUPAC one, okay? Which is the International Union of Pure and Applied Chemistry. The other one I'm going to talk about is this one here, which is an example of something you could find on like the internet. You'll see ones like this quite often, actually. They have more information, more complex. So that's the periodic table of elements. It's going to list the elements that we've encountered. So far, they've only been on Earth that we've really been encountering these things. And for everything we found somewhere else, sometimes we have found some stuff in signals and stuff and other places, but we found it on Earth too. Okay. We haven't found anything. None on Earth yet, or made it on Earth. So Now, these periodic table, this is going to consist of a bunch of little blocks there, and you can see they have chemical symbols in those. Those are those 2-letter codes you see everywhere there. If you find an older periodic table, it might have 3-letter codes, and sometime in the future, there will probably be new periodic tables with 3-letter codes. And what those 3-letter codes are is they are unnamed elements. They've given a temporary name to them. They have a system by which they give temporary names. Then what happens is IUPAC meets and they give it an official name. Okay, typically honoring someone, something. Oftentimes, the person that discovered it can propose something. And so what ends up happening is if you look at ones that were like a decade or so old and past that, they had a half of that bottom row almost that were 3-letter codes, and that's because IUPAC, as my advisor used to call them, are childless, stupid bastards. My advisor hated them. He was old enough that he had the right that he could, but I am not. I don't get to do those things. So they are scientists get in fights just like everybody else, and IUPAC is notorious for this, and so they got into a fight and did not meet for about a decade. Okay, and that meant half a bottom row didn't get filled in, so we discovered a bunch of elements and made a bunch of elements. Now, if you look at this periodic table up here, a lot of periodic tables don't have this. It's kind of nice. See the ones that have like the outline but not filled in? Okay. Those are man-made elements. We have not found them in nature. Okay. We find them in nature, they get filled in. Okay. So those ones have never been found in nature, and typically they're considered what's called the trans-uranium. See how they're after uranium? Yeah. Now, one of the things I need to point out for this periodic table before we go much further, and this is actually one of those shameful things. You can look it up. I've stopped trying to put it into my PowerPoint because it doesn't, you can't read anything on it when I put it in, and so it's absolutely useless. Is that, see this bottom part here? Right here? It's called the lanthanide series. That is not on the bottom of the periodic table like that. Okay? That's not where it actually is. Okay? It is inserted right there. So you take that and you insert it right here. Okay? And that's actually where that is located. It was never meant to be on the bottom of the periodic table. It just wasn't really any other place they could put it, right? The reason for that is if I insert that, notice it lengthens this periodic table almost double, right? And so everything has to shrink down because it's so dang wide, and you can't read it, okay? This is one of the nice things about physical textbooks is the old physical textbooks, actually, they'd have a fold-out periodic table. And so it would be cut in such a way with the page, it would be folded up in such a way that would literally just fold out and you'd have this where it's supposed to be, okay? You can look them up. It takes some work because or a widescreen. You have one of those ultra wide screens. It's nice. And you can see what that looks like. Okay. Now the names for the elements. These names for these elements are a little bit strange. You might notice. Okay. So carbon is C. That makes some sense. Boron is B. That makes sense. Sodium is nitrogen is N, oxygen is F, fluoride is F. Oxygen is O, fluoride is F. Okay. All of them make sense, right? Looking good. Okay. How about gold? There's no G things. Where the heck did gold go? Well, gold is aurum. Okay. And that's because back in the day, to be a qualified scientist, you would speak your native language. And then for time periods, you might have spoke French, English, German, but those were always short time periods. However, until about 1970s, you spoke, no matter what, Latin and Greek. Okay? And so you spoke Latin and Greek, and when you went, I don't know what I'm going to call gold. I don't, G doesn't work there. You went aurum, because that's gold in Latin. Okay? Or argenta, silver. Okay. Has everybody heard the saying silver and blood? You can pay in silver or blood? No? Okay. Basically, it was a fancy way to stick somebody up. So you either give me the money or you die. So, but you sounded real fancy, and people were less likely to be angry at you because man, he sounded polished. So you ever want to stick someone up? I expect. Uh, what is that? I forget how to say it in Latin. It's been a while. But essentially, what it boils down to in English is silver or gold, or you feel wet. And say that in Latin. People will be so impressed, they won't care. All right. So, sodium, natrium, that's the Latin for that. The one you all know, and I know you know this, has anybody heard of plumbing before? Oh my God, nobody's heard of plumbing? We got some problems in this class. You've all heard of plumbing, right? Come on, commit. Be alive. The sad part is every now and then I do run into people that are like, no, I've never seen a beach. How is that possible? Damn movie or something. I don't know. Go to the beach like what? There's 1 hour from here or something. I know there's one in Paris. Um. So, everybody, look over here at 82, please. PV. Okay, that's uh plumbing, plumbous. That's the Latin word for lead, and that's because plumbing was traditionally made out of lead. And in fact, there's still a lot of plumbing applications that use it. So they call plumbing after plumbous lead. Okay. And so that's lead. You will note that that's actually the last element that before we get into the radioactive stuff. So it's all sorts of interesting and helpful. So groups, you may notice that we had numbers on the top of this and numbers on the top of this one. Those were our groups. So if we look at those groups, they group up nicely as we go downwards, okay, up and down, into things that are very similar, right? You will note that copper, Cu, by the way, there are a few that are kind of outliers like Fe, iron, ferrous, copper, cuprous, which is copper, Cu. And those were actually mythological names that basically the scientists that found it and identified it wanted to do something interesting. Typically, it's for things that they were already used or named and they needed to just find something. Okay? Or they were done a long time ago. And, there weren't that many elements. There's like 20, 30 of them. So it wasn't that big of a deal to remember all. But so those are actually like I forget exactly which. I think they're both German deities. One is I think Copper Cuprous, if I remember correctly, is the one that's like a fire deity. But there's actually some pretty cool stories to a number of the elements. If you're ever interested, there's actually a podcast that goes into that stuff. So you can actually look that up. Kind of interesting stuff, actually. Alexander Pope is actually in my lineage for PhDs. He actually identified 20 of the first elements. So that's where my PhDs come from. My PhD. All right. So not directly, like I'm not that old. Not even close. All right. So groups, these are going to be the vertical ones. You may notice that like copper, silver, and gold, all of those are like jewelry metals. They also make coinage out of them because they all have very similar chemical properties. Okay. And so that's what you're going to notice for the groups. They're going to have similar chemical behaviors for those groups. Okay. And so you also will notice the groups have different ways in numbering them. Up there, we have the official IUPAC way, which is 1 through 18 for the groups, those columns. And that's kind of nice. But this right here is one of the ones you can find on the internet for periodic tables, and you will see it goes 1A, 2A, 3A over here. That's not the same place that 3 is. Okay. And so A stands for the main group elements. And the reason they do that is if you actually look up to here, this is about 90-something% of all mass in the solar system. Okay? This right here is over 70% of all mass in the solar system. Then the majority of the solar system is right here, hydrogen and helium. And so you can kind of tell that most chemistry that happens in most situations only require those elements. We don't actually use the rest of the elements for most chemistry. Okay? So those are called the main group elements. Those ones in the middle, they're in the middle here. Those are the transition elements. Okay? Then this is the lanthanide series. This stuff's really rare. This stuff only exists, some of this stuff only exists for fractions of a fraction of a second. Like microseconds, faster than human can respond. Okay? Uranium actually exists for millions of years. So that one exists for a long time. But that's what you're looking for there. So the B are the transition elements. You will notice when you start looking at these Bs, see how 8B here is multiple different groups, isn't it? That's because the transition elements have a lot more similarities in there. There are a lot more kind of tiny differences. Okay? And so this is the catalytic triad right there. Very useful metals for like catalysis reactions. And so you'll notice that if you actually look in here, these are metals that you would see in like catalytic converters and stuff. Okay? You see a lot of those in there. And so catalytic triad. Okay? Sometimes you will see these as Roman numerals instead. Instead of a 3B, you'll see Roman numeral 3. Okay? And that's why you'll see them as not like individual group numbers sometimes. Is because they have similar chemical properties in those groups. Now, horizontal. This is going to be known as periods, okay? Because this is where you get your repeated patterns showing up, don't you? Okay. And so periods are going to be numbered 1 through 7. You will notice that ends at 7 right now. Okay. If we ever finally discover the next element, we're going to have to add an 8. And then this book's going to be out of date that bad. Not that anybody will probably care, because you guys, when are you going to encounter it, right? You're going to go inside the Large Hadron Collider and be like, hey, let me eat that one. See what that does to me. So, what you'll notice is if we look at this periodic table here, for some reason that one doesn't have it, there's this stair steps right here. See that? Okay. So these blue things right here, those are metals. Gray things, nobody knows. They don't exist long enough to react. Okay? We can kind of guess, but that's about it. You will notice that that periodic table is newer than the one that your book used. Okay, your book's not super new. And so there are things about the book that's going to be slightly out of date, but to be fair, like you guys are ever going to encounter those right there, right? So this is more like a oriented towards nursing, health, science, chemistry. Okay. Okay. And so right here we see the stair steps. This is where you transition from metals over here to not metals, which are called non-metals right there. Literally things that aren't metal. Okay. This stuff right here, see the stuff in green? These are what are called and considered metalloids. Okay. And so they're going to be things that are kind of metals, kind of, but don't have all the properties. Okay. And what you're going to see here is that the rules by which metalloids operate are heavily contested, and it is a bit of it's one of those things that like every 5 to 10 years, somebody comes up with a new test, and now something that used to be a metalloid is no longer a metalloid, something that used to be a metal is now a non-metal, whatever. Okay? And that's just know that these things, they're kind of metal, kind of not metal. Okay. As of the publication of this book, when this book was published, aluminum was a metal, boron was a metalloid. Okay. Typically, everything that touches on two sides that line is considered a metalloid. Okay. Now, having said that, I'm going to test you on this book. Okay. So if it was current during this book, boron is a metalloid. Aluminum is a metal. Okay. I'm not going to expect you to stay up with the most current research and arguments. By the way, is aluminum a metalloid? Boron, is that non-metal now? Just it's not worth you trying to deal with that. So remember, aluminum is the exception. Everything else that touches the line, that's metal. Boron will be the start of that transition that separates the metal to the non-metal. Okay. Now, that lanthanide series at the very bottom, what rows are those in, or what periods were those in? 6 and 7, right? Because they're up in the periodic table. Okay, they're not separate. They're 6 and 7. That's not 8 and 9. Okay. So there are elements that are important for human health. There's actually a number of them. The ones that are needed in the largest quantity are going to be carbon, hydrogen, oxygen, and nitrogen. These are going to make up the vast majority of your mass, and the most biological molecules get made out of those. Macronutrients are the next one. Macro meaning we need more of those. Okay. And so these are going to be things that you need at quantities greater than 100 milligrams per day. And they're going to be things like sodium, magnesium, potassium, calcium, and chlorine. So you need greater than 100 milligrams a day. Does anybody have any idea how much 100 milligrams a day is? So a gram would be less than a M&M. Okay, an M&M would be greater than a gram. Okay, you need 1/10 of that. Okay, so that's about how much you need of this. That's why you don't need a lot of salt, sodium chloride, right, on your food. You usually get more than enough. But an interesting weird factoid is, do you guys know what the limiting to human growth was throughout all of human history except for the last 200 years? Salt. People couldn't get salt. It's hard to get. Salt was very expensive. And so you literally had failed villages and societies based on salt. And now we're like, no thanks. I'm not wanting any of that junk. So micronutrients, micro meaning small, right? And so we're going to have quantities less than 100 milligrams per day. They'll include things like iodine, fluorine, iron, zinc. There's other elements that are even smaller quantities that we're not going to go into right now, or at least we're not going to go into all of it anyways. But you can actually see reports if you're interested. Okay. But did you think fluorine was something you need in your diet? Same fluorine and fluoride, like your toothpaste? I didn't think so, did you? Yeah. So you do need a small amount of in your diet. Most of these micronutrients are something you need so small amount of that just incidentally you'll end up getting it. Like if you eat any other living organism, you'll probably get it. Okay? You eat a fly, you're probably going to get this. Okay? So you're very, very likely you're going to run into this even if you don't. For reference, does anybody know that vitamins have never had a single scientific study proving that they help people at all? Not one. So the majority of people in a modern-ish society, that has a food available that you can like just randomly select what you want, are gonna get enough of almost everything. There pretty rare. You have to really, really like, I only eat macaroni and cheese every day. Or like students. Students are actually the worst ones. Did you guys know that? Okay. Do you guys know what scurvy is? Yeah. Okay. Happens when you don't eat enough vitamin C, and your body can no longer fight off certain types of infections, which is the scurvy. And the scurvy is actually most commonly seen in the United States in college students. Because y'all eat pizza and Chick-fil-A every day. And don't eat any fruits, right? And vitamin C you have to eat every day because it's a water soluble. You'll urinate it out. So we'll talk more about that later. But these micronutrients, frankly speaking, you could eat this once every like month or two, and you probably are going to be okay-ish. And as long as you're eating a variety of foods, you're almost certainly going to get them. Iodine's kind of interesting. It's only used in one place, your thyroid. And so you do need a little bit of iodine. That's why they iodize the salt. And incidentally, you can get the iodine quite easily if you eat anything salt. So, yeah. This right here is going to be your most common elements. The vast majority of your mass is this stuff here. And then you have your micronutrients, purple, and then your macronutrients here. And you're going to kind of see that overall, it's kind of just the trend of what's available in your environment, isn't it? Yeah. This stuff's more available, easier to find. And then we get down to here. These are a little harder to find. And then this stuff is harder to even find. Okay. So, pure substance is going to contain two or more chemically combined elements. That's going to be a compound. Compounds are going to combine elements in specific ratios. And you already kind of knew this, but you may not have actually conceptually realized it yet. Is that chemical formulas are going to show that water, for example, H2O, is composed of 2 particles of hydrogen, 1 particle of oxygen in there, right? Table salt, NaCl, is going to have 1 sodium for every 1 chlorine. Okay, and that's the ratio it's in all the time. Now, these chemical formulas are going to identify which elements and how many atoms of each element are present in a compound. Okay, so I got a little bit of a joke for you, and then I have not a joke that is just funny, but so freaking scary for our futures. So I'm hanging out with my friends. I'm in the other room, and I'm handling my my business in the other room there. And so I yell into the rest of my friends, "Hey, everybody, do you guys want some H2O too?" And everybody goes, yeah, I want some H2O too. And so I bring it out to them in the containers, and they drink it, and they all go to the hospital and end up dying. And so I don't think it's fair that they're trying to prosecute me. Now, why the heck did that happen? I'm not trying to kill my friends. It's not fair. Got it. So instead of having H2O, 2 hydrogens for every oxygen, right? I had said, do you want H2O too? They took it as well. But I said hydrogen peroxide. Okay. And then those idiots drank it, right? So, no, I'm teasing. Obviously, I did not poison all my friends with hydrogen peroxide. But that's a little joke to try to help you remember this, right? Now, here's not the joke. It's funny, but oh my god, this is something. So does anybody know what Greenpeace is? Okay. It's the best funded green organization on the planet. It pulls in about $14 billion a year. Okay. So it is an organization that regularly meets with and lobbies Congress people. It sets policy. It is probably the single most powerful green organization on the planet. Okay. I don't know if they have it on their website anymore. I've stopped bothering to check because I don't want to read any more stupid shit from them. But I had a student actually present this to me, reference their website. And this was not even, this is a science major. This is the sad part. And what they told me is, and I checked their website and they had this, and as of 2 years ago, they had still had this, so they might still have it, is that the carbon dioxide, CO2, right? The carbon dioxide that comes out of a car, that comes out of a human being, that's bad for the environment. The carbon dioxide that comes out of a plant, that comes out of the rainforest, is good for the environment. They may see a problem there. It's carbon dioxide either way. It doesn't matter where it comes from. It is what it is. Okay? If I give you TNT from an ethically sourced factory and blow it up on you, or I give you TNT from, wherever and blow it up on you, you don't care it blew up on you, right? It doesn't matter where it comes from. If it's carbon dioxide, CO2, it has the same chemical formula, right? It's the same compound, it does the same things. It doesn't matter where it comes from. And so it is no more harmful or less harmful from the sources. That's silly. That's idiotic. It's like a fundamental misunderstanding of science and chemistry on the deepest, lowest levels. That was on their public facing website for like 7 years. I don't know what to tell you there. That's terrifying, right? That they have anything to do with policy. And like CO2, big environmental policy issue, right? That's the organization that like is getting $14 billion a year despite they're ones. Oh my god. Just kill me. This is the craziest timeline, that's for sure. All right. So anyways, so let's talk about physical changes. Now we have our chemical formulas. And hopefully you all, if you're in a position where you get $14 billion a year, will know the difference. Be able to go, CO2 doesn't matter where it comes from. And get them to actually publish something that makes any damn sense. No, again, to reinforce, if I change the chemical formula for something, it changes the compound, right? So if I were to breathe, and if I say I breathe out CO, would I be okay? No, that's carbon monoxide. I would have choked to death and I'm dying. Okay? Okay? I'm breathing O3 right now. Anybody know what O3 is? Ozone. I'm gonna die in 10 minutes. Okay? I'm already dead, actually. I've been talking a lot. O2 is the gas I'm breathing right now. And O4, I would have blown up here because that's an explosive. So O4 is very explosive, very high energy. That would have taken me out and probably all of you with me. Okay? So that one's not happening. This one right here, physical change. This is going to represent a change in the state of matter is one of the most common things, but it's going to be a change where the form of the matter is changed, but the identity remains the same. Okay? And so you don't change what it is in terms of its identity. So if it was O2, it's still O2. If it was H2O, it's still H2O, right? You change the form of it. So for example, ice cube melting, I still have water at the end of that, right? I freeze the ice cube, I still have water at the end of that, right? I break the ice cube, I still have water at the end of that, right? Those things are all physical changes, right? I tear my page, still have paper, don't I? Write on the page, still have paper, don't I? Dissolve sugar, all of a sudden I don't get killed by the sugar, except for maybe like 50 years from now. But, it's still sugar, isn't it? In that water. And I could get that back, okay? And so those are physical changes, right? Chemical changes. These are going to be things that are going to change your chemical identity of that substance. So the stereotypical example is burning things, because that's super obvious, right? I burn coal, I don't even have a solid stuff at the end. I have gases that come out of that, and they're carbon dioxide, and depending on how pure the coal, it could just be carbon dioxide, but it can be some other stuff too if it's not very pure. Hydrocarbons like gasoline, I'm going to have carbon dioxide and water coming out at the end. It is not the fuel coming out at the other end of that car, is it? I'm going to have more gasoline coming out and recollect it. No. So those are chemical changes. We're going to change the identity of the substance. You burn sugar and you no longer have sugar, right? It doesn't taste sweet, doesn't taste like sugar. Okay? In case anybody wants to argue this with me, caramel is not burned sugar. Okay? That's just not true. Okay. All right. Anybody have any other does everybody understand the difference between physical and chemical change? Do you have any questions there? If I eat food, what happens to that food that I urinate out? Partially, some of it dissolves, and like that's your vitamin C. But for example, the urea produced, that's mostly chemical change. So I'm actually taking like proteins and I'm breaking them down. Okay. The stuff I poop out, on the other hand, my fecal matter, that stuff is physical change for the most part. That's going to be stuff I just didn't process. Okay, I passed that through. So, how about breathing? I'm breathing. I'm getting in O2, right? Oxygen. What am I breathing out? CO2, right? Yeah. And so that's a what type of change? Chemical, right? Yeah. I had O2, now I have CO2. Different identity. Okay, so let's talk about chemical equations. These are going to matter a lot for chemical changes. This is what the equation looks like. You'll notice it looks a lot like a math equation. That's because it is. It is a math equation. This is an equal sign. Okay? It very much is. And this is what's called a reaction arrow. It's an equal sign that has a direction to it. Okay? And so what we have is we have variables. And these variables are going to be our chemical compounds. In this case, we have carbon and we have oxygen, which is O2. Okay? And those are going to be like our A, B, C, Ds or X, Y, Zs that we would see in math. Okay? They're going to be our variables. Now, what we're going to see here is this is the reactants on our left side. They're going to be the stuff we put together. And then we're going to have our reaction arrow. It's going to have various different conditions and things that happen here. And so typically it's conditions this reaction has to undergo. In this case, we need to provide heat to start this off, and then it produces its own heat, doesn't it? Okay? Because it's burning coal. And we have our reaction arrow here. This right here is going to be our products. This is what we're going to produce from this reaction. Okay? And so we're going to produce here CO2 from burning pure coal. Very unusual to find actual pure coal that burns so clean, but apparently that's what we're getting. All right. This S here, well, stands for solid, doesn't it? Okay. If we saw an L, that would stand for liquid, right? Okay. That G there, that stands for gas. Yeah. AQ is aqueous. Anybody know what aqueous means? That's a tougher one. It sounds like aqua, doesn't it? Exactly. Yeah. Aqua is in water, so aqueous dissolved in water. Yeah. You got it. Now, it is considered a phase. It is not one of the stereotypical states of matter that you would have thought of. Anybody know what the states of matter are? Solid, liquid, gas. Got it. Anybody know any other states of matter? Plasma. Yep, plasma is another state of matter. Typically seen in things like blowtorches or lightning. Okay, that's where you'd see it on the planet. Otherwise, the sun, big plasma ball. Very big. There's other ones too. We're just not going to go into the plasma and all the ones that are really, really unusual because you're just not going to interact with them. Okay. If you're interacting with plasma, you probably have bigger problems to think about than my science class. There's other things though, like boson-Einstein condensates, and you can get some other weird stuff going on. But we're not going to. We don't have that short time. So this right here, we're going to have to balance chemical equations. You may have heard of the law of conservation of mass. Now, this is actually a really fascinating difference between ancient people and modern people, actually. Is that now you all probably think the modern thing, okay? Which is that the law of conservation of mass. That's your baseline assumption. So I don't actually create or destroy anything, do I? I just change things, okay? And so if I check in my bag, I have the things that were put in my bag. They may break, they may get snipped, they may change, they may tangle, they may different changes, right? But I do not suddenly have a gold bar in here, do I? Okay? If I was an ancient person, I would close this up, I'd let it get out of my sight, and then I would think that anything could be created at any time as long as I'm not viewing it. That was a mind thought of an ancient person. And so I open the bag back up, goblin. Open it back up, dragon. Open it back up, gold. Nothing. Food. Bacteria. And so they're into bacteria, but you get the point. That's why there's like here be dragons on maps and stuff like that, because they thought that things could be created or destroyed. Like disease and rot could just pop up. And it just came from nowhere. Okay? It's very difficult to find a human being on this planet now that thinks that way, because this law of conservation of mass is such a fundamental belief to modern people that if they've had any contact with modern people, it gets transferred. Okay? And so it is really hard to find that, but you can still find it in like kids and stuff before they learn, and it acclimatize to them. But it's really kind of an interesting, crazy, fascinating thing, right? You can't even fathom thinking like that, can you? It's like, how? So when we look at these reactions, one of the things you have to understand about these reactions is they have to be balanced, right? We can't create or destroy things. We can only change them. And so the number of carbons I have on both sides of this reaction always has to be the same, neither less nor more. If I have one carbon, the other side has to have exactly one carbon, right? If I'm positively charged, I have to be positively charged. If I'm negatively charged overall, I have to be negatively charged. The mass on the reactants, I have to have the same mass products. Can't create or destroy anything. I can lose it, maybe. I can whoops, I don't know where I put it, but I can't create or destroy it, right? And so what that tells us is these things that we've just put together, we need something called coefficients. It's the exact same thing as math, right? When we want two x's, we don't go x squared or x to the subscore 2 or some weird thing, right? We don't go xx. We go 2x, right? 3x. We want 3x's. And so we're going to do the exact same thing. That's the coefficient of x. We're going to put coefficients for our variables, which are going to be carbon dioxide, oxygen, carbon, right? We're going to have our compounds, our elements. And so one of the things I have to warn about and warn you against, and this is going to be something somebody's going to have an issue with, but if I had two of these oxygens, right? If I want to represent two of these oxygens right here, I have to put a 2 in front of it and then O2, right? What would be O4? Could I just do O4? No, it'd be a whole different compound, right? It's actually explosive. You do not want to breathe O4. I don't care how much oxygen you want, you do not want O4. Okay? Very reactive. And so 2 O2s mean I have 2 of those oxygens I'm breathing, right? 4 O2s means I have 4 of them. Just like my example with H2O2, right? I don't want to drink H2O2. Even if I wanted some more oxygens, I need to do 2H2Os, right? That gives me 2 waters. And so be very careful about changing these subscripts, because when you change subscripts, you change chemical identity, right? It's an entirely different compound, okay? Now, that's the coefficients. I'm going to mention these only once, and then I'll never mention this thing again, which is I have these steps that I put in, and they're like routine steps that you can follow to solve that exact question. The problem I find is that 2 problems. Number one, a majority of students that I've done this with just do not find it helpful at all. They find it, now I need to memorize 3 things to do something simple. What the hell, Dr. Clausen? But beyond that, I find that students that do learn this way can have a habit of not being able to perform any other problems than that. So if it deviates at all, they will not be able to do it because it doesn't perfectly match up with the steps. Like if I suddenly give you a pre-step that you would have to do, like you have to do a different small operation, that just falls apart. And they don't think of it as something you can plug and play after another thing. They think of it as like, this is the only problem I can do. And it's really kind of a pain in the butt. But I give it to you because I do find there's like a maybe 5th or a 10th of the students that actually find these very, very useful. Okay. And so there you go. Never mention it again. They'll be there. Okay. Kind of like my thing at the very beginning. I have like a little chapter structure. It tells you what each section in the chapter is. Never going to talk about it. It's there for you to help you out if you want to go, where's the chemical formula stuff in my chapters? Okay, it's right there. Now, for measurements to be easily compared, we have to define a measurement system that was necessary. This was actually a really interesting story that happened in France. You had 2 universities across the river from each other, and they literally were just kitty corner. You could throw a rock from one into the other's window. And they had entirely different unit systems. And so they would actually meet at like bars and they'd talk about this, what I'm doing. And then the other guy would go, yeah, I'm doing something similar, but I got this result. And then they'd get into fights and they'd have the same damn result because they didn't have any of the same units, right? It'd be like you going, I'm a billionaire. I'm a billionaire. I have tens of billions in my account in Zimbabwe dollars. And so if you don't know, that's like a few $10. So it is absolutely meaningless to discuss without units, right? Without units, nothing makes sense. So the Système International des Units, SI, this is the modern day version. This is actually the modern day way of setting these units. The metric system is a slightly different concept, which is that it's an applied version of these units. Most of these units are the same for the metric system, for like nations and people. Okay. Anybody know when we are supposed to transfer to the metric system? It kept getting pushed out, but between 1970 and 1984. Doing good. So, standard unit of mass in the SI units is going to be the kilogram. Standard unit for volume is going to be the liter. Standard unit for length is actually the meter. Mm-hmm.
Do you think we should flip the metric system, or do you think we should?
You know what? I don't think it matters, to be honest. Like, it really just doesn't matter. As long as you have, so the current imperial system, which is what we have, which was actually French originally, is currently based on the SI unit anyways. And so is the metric system. And so if we're really talking in terms of science and everything, the only thing not being on the metric system does is confuse Canadians. That's it. They have to learn 2 units because they're so heavily influenced by us. That is basically it. We have such a large market here that it really doesn't matter that people have to like make things that say feet, whatever. Nobody cares. Yeah. And we would have had a differentiation in market anyways. So I would personally like it to be on the metric system. Like personally, I think it would make teaching science slightly easier, and I just like the metric system better. I don't like that like feet versus inches, and how 12. Why 12? It's annoying. And then a foot is a French king, his foot, and screw the French kings. So, so yeah, there's a lot of things about the imperial system that I just find annoying. Metric system for me is much easier to use, but I don't think it really matters, to be honest. I get why they didn't bother. Yeah. So in the metrics, well, actually, in any system, it doesn't matter. You can do this for anything. But in the metric system and the international SI system, they commonly use prefixes. Okay. And you've already been using prefixes. There can be units of powers of 10. And so you can multiply or divide your numbers by 10 by putting these prefixes. It makes for a really, really fast and easy way to reference large and small numbers. Okay. And we do it all the time, everywhere. You just kind of didn't know what the heck was happening in your life before this. Okay. Giga. Everybody's heard giga before. Gigahertz. 5G, 4G, 3G, 2G. Yeah. Those are gigahertz numbers. And then you've heard probably gigabytes, like drives and stuff. And that is a billion. So a gigabyte is a billion bytes. Okay, gigahertz, a billion hertz, right? And so mega, that's the next one you've probably heard, probably megabits from your internet company. Notice the difference between bits and bytes, by the way. They give you those numbers because in every byte, there's 8 bits. So they can give you a number 8 times larger, and you go, man, I got a great deal. That's really fast. I'll be able to download that DVD so fast. And no, no, you can't download the movie that fast because the number you think you have is 8 times larger than it actually is. So ISPs, man. Did you know we paid them almost $500 billion for fiber everywhere in the United States and did not see almost any of that? Yeah. Yeah. Look it up sometimes. It is wild. Talk about just government mismanaged combined with corporations being way the hell smarter than the government. Just wow. So, oh man. Killing me here. Now, mega, that is 1 million. So if I had a mega dollar, how much dollars would I have? 1 million. That'd be a really nice count, right? So kilo, if I want to get paid 100K, what am I trying to get paid? Yeah, 100,000. Yeah. So kilo is 1,000, right? You already knew that. You were saying that all the time. You've used that. And so that is 1,000 times, like a kilogram is 1,000 grams. A kilo dollar is what you're using when you say 100K. That is $1,000 for each one, so $100,000 total, right? And so I want to get paid 10K for this kilo of I think Coke is 10K right now, probably. I don't know. Anybody know? Thank you for not outing it. So if I had to guess, it's probably cocaine. It's probably 10K kilo right now. But a kilo of something would be a kilogram, right? Yeah. And so that's 1,000 grams of that. Okay. Now the base unit, these will have no prefixes. It's actually really funny because there's a lot of people, like everybody thinks that Europeans are so smart, blah, blah, blah. I've actually run into a number of Europeans. They do not know this, that think the kilogram is the base unit. It is not. It is kilo, 1,000 grams, grams being the base unit, right? And so deci, 1/10, right? That's decimeter is 1/10 of a meter. And so to be fair to Europeans, plenty of them are smart. They're, of course, like any other group, are morons. Or just uneducated. Honestly, that person was just uneducated. So they learned that later in my class. So, centi, this is going to be a centimeter, and so that is 1/100th. Now you can turn these around, of course, and you can go, there's 100 centimeters in 1 meter, right? So if I have 100 centimeters, I have 1 meter. If I have $1,000, I have a kilodollar, right? Okay. Now, if I have a milli, you may have all heard a milliliter, right? Everybody's heard a milliliter? Yeah. Okay, good. Millipede. All right, so milli means 1,000. So if I have a millimeter, then I have 1,000th of a meter, right? Milliliter is 1,000th of a liter. Okay, and then we've gotten centi and milli now. Anybody know what a cc is? Quick stat: 100 cc's. Cubic centimeter. You got it. Yeah. So that is a cube that has a centimeter on each side. Okay. If I wanted to say that in another volume term, well, what would that be? 1 cc would be the same as what? No? Nobody? 1 milliliter. Okay, that's the same as milliliter. And so that again is the definition actually of a milliliter. Okay, and so that's 1,000th of a liter, and that would be a cc, a centimeter cubed, or milliliter. Now, micro.
Do you know why they use CC instead?
Okay, so it has to do with several different units were used at the time, and a lot of this was okay. So doctors are called doctors because of people like me. So back in the day when it first started, doctors were very well-educated natural science people that were PhDs in chemistry and biology sciences. Okay. And so then they would perform medical procedures with the chemicals they made themselves. Okay. And so that has since then been subdivided into pharmacists, doctors, nurses, all these people, right? The physical surgery part was actually taken care of by barbers. So you've taken two occupations, you put them together, gave them medical licenses, and called them doctors when they had no right to be called doctor. So very strange. But so the reason that these are called CC some places is this was originally scientists doing this, and they sometimes did things in cubic centimeters because it was easier to measure centimeter. And then milliliter, they actually a milliliter, a liter is a deciliter on each side. And so that was originally what a liter was. It then had its own name, and then milliliter transferred through. And so it's just been sort of a confusion of terms since then that kind of goes back and forth in different countries. So micro like a micrometer. So micrometer is going to be 1/1,000,000th of something. So if you have a micrometer, it's a millionth of a meter. And so that's like microprocessors are measured in micrometers. Okay. A microliter would be 1,000th of a milliliter. Okay. Very small amount. And so this is a mu symbol here, or you can put MC. Now I want to show you guys something that's very important for your not dying. Okay. So keep in mind microbiology is measured in micrometers, right? That's where that comes from. It's biology on the micrometer scale. Okay. So let's say I'm at the hospital and the doctor writes in the chart, he's really writing quick, and doctors have terrible handwriting anyways, right? And so this is the symbol you should write, or actually liter, excuse me, for a microliter, right? Let's say you're doing it real quick and you write that. What does that kind of look like? So, one of the most common malpractice things that happens, and I get stopped. I've taught nursing chemistry for like 15, closer to 17 years now. And so I get stopped in like the middle of the aisle in Walmart by former students and are like, Dr. Clausen, you were exactly right. Somebody tried to do this and I stopped them and kept this person from doing something stupid and killing somebody. Okay. And what it is you guys know there's the machines, right? You can dial in the amount of morphine or any drug really, but morphine being the one you probably are thinking about. Okay. And being one that's very dangerous. Okay? And so the nurse sees that, then comes up to the machine and starts dialing that. This right here is 1,000 times the dose. Okay? And so what happens is the nurse sits there, click, 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 beep, 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 beep. Dang it. I need to get my card and do this. And they start doing that. If they let them, they're going to give you 1,000 times the dose of morphine. You are dead. Okay? You're already dead and you don't know it. It'll be a very peaceful, very relaxed death. But you're dead, okay? They've done this to my PhD advisor, actually. They came up, the machine started going off, and they started trying to deactivate that. And he goes, wait a second, I need to see that chart. He grabs the chart from them and goes, here, you need to go check that this is what the doctor wanted me to dose. I think they wanted microliters. This is milliliters you're trying to do on me. And she said no and was arguing with him. And no, I'm going to give you this damn dose. I'm too busy. He ripped the line out, threw it on the ground, and said, no, you will fucking go see your doctor right now. And she was right, of course. She tried to dose him 1,000 times. And I've had somewhere around 20 people, maybe a little less, maybe a little more, come up to me and say, yeah, Dr. Clausen, you're exactly right. I was on the floor and I had a senior nurse and she tried to do this. And so if you ever hear that machine start going off, or if they start clicking more than 10 times, you need to go check your damn chart. That's a lot. Okay? You check that damn chart. I do not want to drift off into peaceful nothingness. Thank you. I don't want to die. Go check the doctor. Okay? You would be shocked about how often this happens. Very common medical malpractice. Does not get caught all the time. People get killed. It happens. Okay? And I know 3 people that caught nurses trying to do this to them. So yeah, they're busy. They don't always think things through when they're doing them. They can't, and it's just tough. Okay? And so you being the nurse, if you're a nurse, double check. You being a patient, double check. Everybody double checks, keeps that from happening, right? Okay. Nano. This is going to be 1 billion. Okay, so if you have a nano drop, it's 1 billionth of a drop. If you have a nanometer, it's 1 billionth of a meter. It's the sort of sizes that you start seeing like atoms. Okay, nanometers are very, very small. Nanoprocessor would be measured on nanometers, usually like hundreds or tens of nanometers. Still. So equivalent units, these are going to be units. They're actually the same thing. Okay. So 1 deciliter is the same thing as saying 0.1 liter. Okay. Now, first off, I need to mention this. Does everybody know that is the same number? And if you don't know, please talk to me, because we need to actually do some math review stuff, okay? If you were to talk to me, you would be like my 6th or 7th person I've had to deal with this and figure out math issues, okay? not at this university, but overall in my career. And so all recently, this is just something that's happened due to unreliable education in the United States. Okay, we'll call this a day. This will be time. That's actually really rude to do that, but whatever. Okay. You guys have a wonderful day, okay? Have an awesome time. Please try to start homeworks and stuff and check those out. Yeah. And I will see you all next time.